Hello, this is the 7th video of the Linear Programming 2 series on the simplex method and integer programming for OCR Discrete Further Mathematics. And we will consider linear programming problems that require integer solutions. We have previously looked at problems requiring integer solutions graphically for two variables and seen that the optimal solution may not lie on the boundary of a feasible region. In the simplest cases, we can evaluate integer pairs close to the boundaries to find the one that gives the maximum value for the objective function. So, for example, we might choose to look at 6, 4, or indeed 4, 6. And we would be able to evaluate the objective function at these coordinates. However, this can become difficult, for example if there are more constraints, and so we want a way to program this to be done using the simplex method, so we can deal with more than two variables. A branch and bound technique will provide a systematic and efficient way of testing integer solutions that might be optimal without having to test all the intercoordinates within a feasible region. We will look at a simple two-dimension case so we can see graphically what is going on, but this method can be applied to much more complicated problems. Here is a formulated two-variable linear programming problem, and we can see that we have the objective function to maximize 5x plus 8y, and then constraints including the non-negativity and the decision variables x and y. Note that in the diagram or graph, the feasible region is shaded. The first step of a branch and bound method is to take away the integer restriction. So in other words, we relax that constraint. And then we solve this relaxed linear programming problem as normal and call the solution LP1. On the diagram you can see that then the x plus y equals 6 and the 5x plus 9y equals 45 intersect at the point A and give us the optimal value of 41.25 for the objective function at the point A, 2.25, 3.75. Because we have relaxed one of the conditions, this is not a valid solution to the original problem. And as we move away from the LP1 solution, we must make sure we stay in the feasible region. Note that the green line is an objective function line and passes out of a feasible region at A. So the branch and bound method involves solving several linear programmings as we go along, which would be tedious by hand, but using computation is relatively straightforward. Looking at the y value at A, we see that we can either have a solution in which y is less than or equal to 3 or y is greater than or equal to 4. So we split the feasible region up to form two possible branches. The two branches are shaded areas as given to find LP2 and LP3. Note that the objective function line in green passes out of a feasible region at the points B and C respectively. We see that LP2 has an optimal solution at B and that B has integer coordinates, so we now know that we don't need to check anywhere else in the grey area for LP2. This means that we can stop at this branch and x equals 3, y equals 3 is a feasible solution with objective value of 39. This could be the optimal integer solution. But we do need to check LP3 as well. And we can see that this has a higher objective function value of 41, but with the optimal solution at C. But C does not have integer values for x. so we need to branch again to look at integer values of x either side of the c 1.8 value. Looking at that x value at c, we can see that we can either have a solution in which x is less than or equal to 1 or x is greater than or equal to 2. So again, we split the feasible region up to form two possible branches. As you can see for the graphs, these would be LP5 and LP4. Now LP5 solution is outside the feasible region, so we do not consider this solution further, and it is said to be infeasible. LP4 gives an optimal solution at 1, 4.44 with objective value of 40.56. This does not have an integer y coordinate, so we need to branch again looking at those y values. So looking at the y value 4.44 at that point D, we can see that we can either have a solution in which y is less than or equal to 4 or y is greater than or equal to 5. So again we split the feasible region up to form two possible branches, LP7, LP6. So LP7 has an objective value of 40 at the point 0.5, which we've called F. And then you have LP6, which has an objective value of 37, and this occurs at the point 1,4 or E. Both of these are integer solutions in the feasible region, hence we will stop. Note that you do not need to do graphs for this method. They've only been used in this video to illustrate the approach. Branch and bound method may be referred to as divide and conquer technique. And the method we have followed can be summarized in a branch and bound diagram. So, given the initial formulated linear programming problem in the red box, if you remember, we started by relaxing that integer condition or constraint and looked at, therefore, the solution to the relaxed problem, LP1, where we got this point A, a non-integer solution, and an objective function value of 41.25. Splitting then into the y values, we then found we had an integer solution, LP2, at the point 33 with p equal 39, and then another option, LP3, which again, because the x coordinate was not integer, we split to look at x less than or equal to 1, x greater than or equal to 2. We found that LP5 was infeasible, so we didn't continue that branch. However, LP4 we split again and then ended up with two more integer solutions. Note that branches stop when we get to an integer solution or an infeasible solution. Now all we need to do is choose the integer solution with the maximum p value. In this case, we can see that that will be p equals 40 at the point 0.5. So this is the optimal integer solution to the original integer linear programming problem given in the red box above. Note that the value is not as high as the optimum solution 41.25, but that was because that value was for a optimal solution non-integer coordinates. This is the final video of a linear programming series 2.